Good evening, everyone. Welcome to the 11th problem solving session of Structural Analysis 1 course. So this problem solving session would hopefully help you solve the assignment number 12, which is the last assignment of the course. The last problem solving session for the course will be held next week. There are no more assignments to be solved, but I hope I will be able to help you with any doubts that you have while you prepare for the final examination on 30th. Let me share my screen. So if you have any particular suggestions regarding what should be covered in the last problem solving session, you please feel free to put it up in the discussion forum or in the YouTube comments. I'm planning to give an overall revision of whatever was covered in the course with a few problems, starting from one of the initial analysis of statically determinate structures, finding deflections, statically indeterminate structures by the force method, displacement method, and also finally this direct stiffness method. So let us get started today's session. Today we'll be looking at this particular method called the direct stiffness method. So earlier we have divided the available methods of analysis of statically determinate indeterminate beams, indeterminate structures into two types. One is the force methods of analysis, and the other is the displacement methods of analysis. So this direct stiffness method, as the name suggests, comes under a displacement method of analysis. It is the thickness. It is a displacement method of analysis where the displacements and rotations at various points are the primary unknowns in the problem. Now, the benefit of this method over the other methods that we have seen in the course so far is that it applies to both statically applies to both statically determinate and indeterminate structures. Unlike the flexibility-based methods, unlike the force methods of analysis, which applies only to statically indeterminate structures, this applies equally to both statically determinate and indeterminate structures. Not only that, be it the slope deflection equation or the displacement or the moment distribution method, we saw that in other displacement based methods, what we have seen, one is the slope deflection equation. And the other one is moment distribution. In both of these methods, we saw that getting the internal reactions, so getting reactions or the shear force or the bending moment was not straightforward. So once we determine the displacements, we had to use a constitutive relation to determine the moments at the joints, and in between we had to do certain equilibrium. We have to enforce equilibrium to get the internal bending moments and shear force, and also for getting the reactions. If you remember, suppose we had a continuous beam like this. So this is statically indeterminate to a very high degree and kinematically indeterminate to the second degree. I have one rotation here and one rotation here. Suppose we had to determine the vertical reaction coming at support B. What did we do? We solved the entire problem. We got a 2x2 system. We've got a 2x2 system where theta B and theta C were unknowns. We solve the system, determine theta B and theta C. Then we determine everything, MAB, MBA, all the moments. Then we considered one span. So then we considered one span at a time and determine the shear force in that span. And if there is any span loading, we had to take care of that also while computing the shear force. And we enforce the equilibrium of joint. We enforce the equilibrium at joint. So we saw at this joint, we have from the beam, you have shear force this way, from the right side beam, you have shear force this way, and you have the reaction this way, and then you set the sum equal to 0, and then you get the reaction at B, which is pretty much complicated. It is not very complicated, but it is very involved that it cannot be directly coded in a computer program. So that is an inconvenience in other displacement-based methods. And force-based methods, it is needless to say that once we get the forces, right, in force-based methods, sorry, not force-based. In force method, the first step itself is difficult. In force method, what was the difficulty? Setting up the matrix system itself is difficult. Because for each of them, we needed a statically admissible set of forces. And statically admissible means we have to ensure that the unknowns that we are considering altogether satisfies equilibrium. So the primary structure we had to solve by equilibrium. The redundant the other ns number of redundant structures had to be solved by equilibrium. Again, that is not computer friendly. So force method cannot be programmed at all. Here we can program it. Displacement-based methods can be programmed, but post-processing, the post-processing of the results to get various internal forces and the support reactions is not straightforward. But in this direct stiffness method, so direct stiffness in the direct stiffness method, we get the displacements and the forces in one step. We get them directly. So that's a huge advantage as compared to the other methods. And of course, the other advantages, it is very much computer friendly. It is programmable. So these are the advantages. So why do we need the direct stiffness method? Because the other methods, force method, it is very difficult to program. Displacement based methods, we can get the displacements by setting up the matrix equations. But beyond that, once we get the displacements, getting the forces is not quite straightforward. Although we have the equations, especially finding the reactions is not quite straightforward. Instead, if we use the direct stiffness methods, we can get all the displacements and the forces directly by solving one system of equations. So that is the huge benefit of this method. And also it is programmable. So it is repetitive. So how is it programmable? How does it help? So the key idea, as we always do, the key idea is that in all the previous methods, we consider the entire structure at once. So we consider all the kinematic variables, all the degrees of freedom, or all the unknown redundant forces at once, and then we solve the resulting system of equations. But the benefit of the direct stiffness method is you subdivide the structure into what we call as members. You subdivide the structure into members and then enforce, not enforce, sorry. And these members are small, simple structural elements, and for them you can write force displacement relations, So write down the force displacement relations for these members. Then you need to assemble them. So the force displacement relations for each member relies on the equilibrium conditions. And when you assemble the members together, you rely on the compatibility conditions. So therefore, instead of considering the entire structure at once, we consider a part of it, enforce the force displacement relations for that small part, and do it for every part, then finally put them all together by an operation called assembly. So this is quite straightforward. So depending on the type of, so if you have a truss, subjected to loads at various points, you don't consider the entire truss at once. You consider each of its members one at a time. So suppose you take this member, you draw this member, indicate the forces. We know that all truss members are two force members. Indicate the forces in that member. Determine what is the force displacement relation. We know that if there's a force acting here F, we know that the extension delta by L is nothing but F by A, which is stress by E. So this is a force displacement relation which is very much simplified for one member. Now this is in some local coordinate axis. It is along the member, some local coordinate axis along the member. We just have to put them together in a consistent form so that you get the force displacement relations for the entire structure. What is the force displacement relation for the entire structure? It is of this form. The forces applied at various points on the structure. So you have one force here, you have one force here. So consider all the joints as nodes. Right? You consider all the joints as nodes. And you have a matrix, a column matrix of nodal forces. So let us call it F. Right? You have a column matrix of nodal forces. Some of the nodes may have zero force also. So in those you have zero entries. That is related to the displacements at all these nodes. Let us call them delta. Or rather, let us take them as D. Let us take the displacements as D. So we need to relate the forces at various nodes to the displacements at various nodes. What is that? What is the component that relates them? It is the stiffness matrix. So this is the key idea. In slope deflection equations or in the moment or in the other displacement based methods, we arrive at a system of linear equations by considering the entire structure at once. In this method also, we will arrive at exactly the same system of equations as the slope deflection method. Of course, the variables are slightly modified, but we arrive at it by considering one member at a time. So that is the key difference between the slope deflection equations and this method. So, and this is suitable for computations because we consider one member at a time and the operations are repetitive instead of, so here, what this method doesn't include, let me tell that. So the benefit, all the benefits come because, let me tell you, we don't need to is Nikhilesh, I think I'm hearing some voice. Can I mute you? Yeah, thank you. So we don't need to draw bending moment diagrams. We don't need to use any virtual work, nor do we have to enforce equilibrium. So that is the biggest advantage of this method. So we directly assemble a matrix called the stiffness matrix, the force vector and the displacement vector, and we get the displacements by solving this system. So that is the benefit. So I hope it's clear. Now, what are the ideas involved? Right? So before we get to the method, the procedure for solving the problem by this method, let us look at some of the ideas that are involved. So as I said, for every element or member, you can use it interchangeably in this course. Later on, it will become very specific. So for every, let me call it member only, you get the force displacement relations. That is quite simple in the case of trusses. In the case of beams also, it is quite simple. Only thing is it will be in the matrix form. In trusses, it is a, in trusses you get a 2x2 matrix, and in beams you get a 4x4 matrix, and in frames you get a 6x6 matrix. But it is completely determined once you know the properties of, so it depends only on the cross-sectional properties and the material properties, and of course the length, orientation, etc. So, but it doesn't depend on loading or the displacements, etc. So that is a very big advantage, which means once you know the cross-sectional properties and the material properties and the length, you know the member, you know the complete force displacement relation of the member, even if you don't for any given loading. So that is the first idea. Then I showed this truss here, right? So how do we know which node is under which force? You need to identify the node. So for identifying the nodes, you do node numbering. You call this node as 1, 2, 3, 4, 5, 6, and so on. So you can number all the nodes for our convenience. So that is one idea. As opposed to, you remember in the force methods of analysis, we take the internal forces as our nodes where we have FAB, FBC, and so on. But here it is more convenient to number the nodes. Once you have numbered the nodes, so you need an idea of the concept of node numbering. So that is not too critical. Then let's go to the next. So that is obvious. Then you need to have a global coordinate system. Why? Because it is always easy to represent the displacements in one coordinate system. For example, if you take an inclined member, if you take an inclined beam like this, let us take a frame like this. And it is fixed in the same. So for this beam, the transverse direction is like this and rotations are like this. For this beam, the transverse direction is like this and the rotations are like this. So when you do it in the slope reflection method, the transverse degree of freedom delta is different in this beam and it is different in this beam. So you cannot add them up directly. This is in a different coordinate system that is oriented this way. And this is in a different coordinate system that is oriented this way. So here in the direct stiffness method, we work with a global coordinate system. That is, once you get the solution, they are all referred to in a global coordinate system. If you set up a coordinate system like this, 1 and 2, all the displacements you'll get U1, V1, U2, V2. That is X and U3, V3, and so on. You get everything in a global coordinate system, which means if you do any superposition, you can just directly add them all up. So that is one idea. You need a global coordinate system to write down the unknowns and the known forces. So these are always represented in a global coordinate system, but you also need a local coordinate system. Why do you need that? Because the member force displacement relations can be written only in the local coordinate system. They are simple to be written in the local coordinate system. So if you take a truss element, if you take it in the general system like this, the force displacement relation is quite involved. But if you take a coordinate system along the member like this, it is very simple. As I said, if you fix this end, the force that needs to be applied here is just EA by L delta if it moves by delta. So in a coordinate system that is oriented along the member, the force displacement relations are simple. FD relations are simple in a local coordinate system. But in a global coordinate system, the force displacement relations are not quite simple, but it is very convenient to represent all the unknowns and the known forces in a global coordinate system. Once you have two coordinate systems, of course, they are not very independent. The quantities that you compute in the local coordinate system are not independent of the quantities that you compute in the global coordinate system, because there should be compatibility and other issues. And forces are vectors, so they transform in a certain way. So you need a transformation between the local and the global coordinate system. So we need transformation rules between the local and the global coordinate system. So once you have all these, you have the local force displacement relations for every member, you have a consistent system of node numbering, you have a global coordinate system, and when you have a local coordinate system, the next step is to put them all together in an assembly operation. So assemble them together, and finally you get F is equal to K times. So this is what you need to get finally. These are all in the global coordinate system. This is the global coordinate system. So K is also in the global coordinate system. So let us see how to go about this. So first, let us take the case of trusses. So this is trusses. The direct stiffness method applied to trusses. As I already said, we know that the truss members are actually loaded. So suppose you have a truss member isolated from the structure. So let us call this as a local node 1, local node 2. Let us call this U1, P1, Q2, P2. And you need to have a local coordinate system. So let me mark the local coordinate system in blue color. So so these are the global degrees of freedom referenced in the pink coordinate system. So you have a coordinate system like this, X and Y. But the member is inclined, so you need to have a local coordinate system. So let us call this U1 prime, U2 prime. And this is with respect to a local coordinate system that is oriented this way. X prime, Y prime. And the angle difference can be taken as this theta. This angle with the horizontal, let's take it as theta. So in such a setting, let us write down the force displacement relations in the local coordinate system. So how do we do it? Let us use the principle of superposition. Suppose there is U1 prime and U2 prime at the same time. So let us first arrest U1 and apply a U2. So let me apply a U2 prime using a force. So let us apply a force F2. And in the next case, so this can be considered as superposition of two cases. The next case, you arrest this and you apply a U1. So that is basically what we are doing. We apply a U1 prime and you have force acting here, F1. But we know that an equal and opposite force will act because trusses are two force members. So here we'll have an F2. Here also you will have an F1. By basic strength of materials analysis, we can easily say that what is the strain? So strain is delta by L. In the first case, it is U2 prime by L. In this case, and here it is U1 prime by L. So it's a minus, it's negative. It's fine. What is the force that is required? So the force is A into sigma, which is A E strain, which is AE by L U2 prime. This is F2. And here, what is F2? Here, F1 is again A sigma. So here sigma is compressive, so you should take the minus sign. So it is minus A into sigma, it is compressive. So it is minus A E minus U prime by L. F1 is also A E U1 prime by. But we know in a stiffness based method, what should F2 be equal to? It is equal to. So you have a force acting at. So this is a joint 1. This is joint 2. This is joint 1. This is joint 2. You have a force acting at 1 due to a displacement which is applied at 2. So this is nothing but K11 U2 prime. And what is this? This is K22 U2 prime. And this is in the other opposite direction. Our coordinate system is like this, so this is minus. And here, what do we have? Here, F1 is equal to K11 U1 prime. And this is in the other direction, so it is minus K21. So you have a force at 2 due to a displacement at 1. K21 U1 prime. Now, what are the total forces? So in the correct sign convention, you have the total force at the node 1 in the local coordinate system is F1 is equal to, let us put a dash, F1 dash is equal to minus K11. Just a minute, this is not K11, this is the force at 1 due to a displacement applied at 2. So this is K12. So minus K12 U2 prime plus K22 sorry. So minus K12 U2 prime plus K11 U1 prime from this. And what is the net force on the node 2? It is minus let us see, just a minute. So F1, the net force in the correct direction, it is actually is nothing but F1 minus F2 because of this, and F2 prime is F2 minus F1. And what is minus F2? It is K11. So here you get it is so this, if you put it in a right form, you get it is AE by L U1 prime minus AE by L U2 prime. Here it is minus AE by L U1 prime plus AE by L U2 prime. So if you write this down in a matrix form, the local forces F1 prime and F2 prime are related to the local displacements U1 prime and U2 prime by this matrix. If we take AE by L commonly out, It's related this way. So this is the local force displacement relationship. But we have to take it back to the global form to assemble and write down the uh, or write down the unknowns and the knowns in the global coordinate system. So how do we do it? We need to transform. So first, let us transform the displacements. Right? So you have 2 points like this. Suppose you displace. So the total displacement is a superposition of a small displacements along the x-axis u1. So suppose this is the and the displacement along the y-axis v1. How are these two related? So how are these two related to the local displacement? So local displacement is something like this. So you drop a perpendicular from here. The displacement along the length of the original member is u1 prime. And even in this case, you drop a perpendicular like this, and the displacement along the length of the original member is u1 prime. So this is in one case, and this has to be superposed. So what is u1 prime in the first case? So it is u1 prime. This angle is theta. This is a 90 degrees. This is a hypotenuse. So it is u1 cos theta. And in this case, it is the angle is 90 minus theta. So this is a hypotenuse. So it plus cos of 90 minus theta, which is sin theta. So we get sin theta. Similarly, u2 prime is u2 cos theta plus v2 sin theta. So this matrix that relates u1 prime, u2 prime to the global degrees of freedom u1, u2, u1, v1, u2, v2 is related by a matrix of what do you have? Cos theta, sin theta. The other entries are 0 because the displacement at 1 cannot depend on displacements at points 2. And this is also cos theta. So this matrix, we call it as the transformation matrix, which relates the local and the global degrees of freedom. Fine. Then, and similarly, we transform the forces as well. So how do the forces transform? So you have, suppose you have a force acting at a point. So you had F1, right? If you have F1, we are interested in the total horizontal and the vertical components. So the horizontal component of F1 is just F1 cos theta. The vertical component is F1 sin theta. So how are the global forces related? So global forces are, you have, let me also draw a diagram of forces. So the force diagram is like this. Locally, you have F1 prime, F2 prime, and globally you have F1x, F1y, F2x, F2y. And from this transformation, F1x, F2x, they're just the components. So I can write this as the global to local relation. F1x, F1y, F2x, F2y. What are they? They are just the components. So you get some, sorry, this is a 4 cross. So they are just the components. So what is F1x? F1x is F1. So and what is it related to? F1 prime and F2 prime. So F1x is F1 prime cos theta plus 0 times F2 prime. So you can write it as cos theta 0. And what is F1y? It is sin theta 0. And F2x cannot depend on F1. So this is also cos theta, sin theta. Note that this matrix is nothing but T transpose. Now let us substitute these into the original force displacement relation that we had. So here, let us write this as F prime column matrix is equal to some local that is called Km times U prime. So this is the system that we are having. And here we have a bigger system. So how sin, what is U prime? U prime is related this way. So here what do we get? We get U prime is this transformation matrix times the global U. And here what do we get? We get F, the global F is transposition of the transformation matrix times the local F. Now we have F prime is equal to some local matrix, local member matrix times U prime. And U prime is nothing but a transformation matrix times U. From this, right, let us multiply both sides by, so let us multiply by T transpose. You have T transpose F prime is equal to T transpose Km T U. So what is this T transpose? T transpose is 4 cross 2. This is 2 cross 1. This is 4 cross 2. This is 2 cross 2. This is 2 cross 4. And this is 4 cross 1. So finally, you get a matrix. So let us call this as F, the global F. That is how we defined it, right? So this is the relationship between these two. So we have the global F is related to the global use by some matrix that is K global. So this is for a truss member. This is 4 cross 1. This is 4 cross 4. And this is 4 cross 1. And they are defined this way as we just saw. So the steps of analysis is simple. Construct. So once you have the nodal, once you have the element properties, the section properties and the material properties, you can construct the member stiffness matrix. And once you have the member stiffness matrix, if you know the orientation of the members, you can transform the stiffness to the global coordinate system from 2 by 2 to this 4 by 2. You do this transformation. Now in the forces, so at some nodes the forces will be unknown, and at some nodes the displacements will be unknown. So if displacements, so we always know that if displacements are known, then forces are unknown, and vice versa. And this is at a point. This is at a point. You can easily see that if you take a beam or any member, at this point the displacement is known. You know that the displacements are equal to 0, but you don't know. In general, you don't know the forces. So before you solve the problem, the force in this is not known. So here the force is unknown, the displacement is known. Here displacement is known. Here also displacement is known, force is unknown. Here also displacement is known, force is unknown. But here what is known? So this will deform like this. Here the force is known, but the displacement is unknown. So if you see the total, so in this some F's are unknown and some U's are unknown, but totally we'll have only 4 unknowns. That is the beauty of this method. So this is for one member, and then the next step is to assemble the members, right? So if you take a node, we have already done the node numbering. It's 1, 2, 3. What are all the members that contribute to the stiffness at the joint 2? 1, is coming from this member and the other is coming from this member. So once you go to a joint, see what are all the stiffness contribution to the joint from the other members. And then add them all up. So that is also a form of superposition only. So that is basically assembly. So as we solve problems, it will become clearer. So the procedure is simple. Identify a global system. So the procedure is identify a global coordinate system, which is the key step before even you solve the problem. Then identify members and nodes. Once you've identified the members and the nodes, it completely specifies the connections between the different members. So that is one thing. Then you need to number the nodes. So that is already done. Get the local force displacement relations. Transform them. Assemble the set of equations. Solve. And that solves the problem. So once you solve, you'll get all the unknown forces and displacements in one shot. So that is a very good thing about this method. So this is for trusses. When we come to beams, the method is the idea is almost the same. There is not much of a difference in this. Okay. So the only place where we differ is identifying the members and the nodes. Because in a truss has no transverse loading. Of members. So a truss member cannot be loaded this way. So that is not a problem. But if it's a beam member, it can support transverse loads. So you need to ensure that you have a node at the location of the transverse load. So if you have a beam element, you ensure that you choose the beam elements such that there are no span loadings, span concentrated loadings. So again, that is just a convenience. So it basically means you have something like this. Don't discretize it as one element. So this is wrong. Because you will not be able to capture the effect of this. We are only dealing with the equilibrium at the nodes, so you will not be able to easily capture the effect of this applied force. So instead put three nodes this way. Instead of two elements. That is the trick. And so that is the only difference. And in the case of frames, also the same thing applies. Further. But this is in the case of concentrated loading. And how does it help in the case of distributed loading? Right. So if you have a distributed span loading, so here you can't put a node everywhere in the beam, right? So in this case, what do you do? So in this case, you apply the principle of superposition. So this is nothing but, so while considering a member subjected to distributed loading, you consider it as a superposition of two cases, where in one case you fix the supports, and what will be the moments that are generated? The moments and the reactions that are generated are like this. This plus this superposed with the other case where you remove the fixed, we apply the negative of the fixed end moments. This. So this can be thought of as a superposition of this one and this one. This will not give rise to any displacements at the joint. So this is so this will not enter our equations because the displacements are all zero in this case. So basically, the relationship between the forces and the displacements are exactly the same in these two cases. So when subjected to a span loading, the way in which the various displacements, various nodal degrees of freedoms are related to each other by the stiffness matrix are exactly the same as if you apply the negative of the fixed end reactions to the same beam. So, right, so that is how you treat these cases. I hope it's clear. Is there any doubt? Okay, let me proceed. Let's get into solve the problem solving. So let's look at the first question. Consider the correct statement in the context of a stable structure. So you need to know what is a positive definite matrix. So let us see what is a positive definite matrix. So in linear algebra, a positive definite matrix is defined as follows. A matrix A is positive definite if and only if, right? So if and only if X transpose AX is greater than 0 for all X that is not equal to 0. So this is a matrix. X is a vector, a column vector. A is a matrix and X is a column vector. So you take any X, right? You take any X n cross 1, which is not equal to 0, that is 0, 0, 0, right? You take any X n cross 1 and pre-multiply X transpose with A and multiply the entire thing with X. So what is this? X is n cross 1. X transpose is 1 cross n. A is say an n cross n matrix. And X is n cross 1. So what is this? This is 1 cross n. This is n cross n cross n cross 1. So this is n cross 1. So you get 1 cross 1, which is a scalar. So since it is a scalar, you can compare it with numbers. So this quantity has to be greater than 0, strictly greater than 0, as long as X is not equal to 0. Now, does our stiffness matrix obey this? So what do you think? Yes, the answer is yes. The stiffness matrix is positive definite. So how do we prove it? So the stiffness matrix is K. What is the size of the stiffness matrix? It is just the number of degrees of freedom, ND cross ND. Now let us take any U, which is ND cross 1. So this is the stiffness matrix. This is any vector of nodal displacements, ND cross 1. Now, in this case, so uh, what is U transpose K U? So this is what we need to compute. But what is U transpose K? What is KU? Let us group it this way. If you group it this way, you get KU. But KU is equal to F, which is the vector of nodal forces. So U transpose F is what? You have U1, U2, and so on up to UN. And you have F1, F2, and so on up to Fn. So this is basically nothing but summation I going from 1 to n ui fi. So u1 f1 plus u2 f2 plus u3 f3, you get one scalar value. But what is this actually equal to? So this is some kind of work done, and we know that for a linear elastic body, if you have a linear elastic body, some force displacement, the work done by a force P is the area under the curve. So for a linear elastic body, the force is proportional to the displacement, and this is nothing but the work done by force P. What is this? This is the work done by all the nodal forces in causing the displacement U. But But you see that the forces increase linearly as the displacements are increasing in a linear elastic body. So the actual work done will be an integral, and since it is linear, you'll get a factor of half. So the strain energy is equal to the work done. Why? That comes from the principle of conservation of energy for structural systems. Right? Well, if you are doing some work, that has to go somewhere, and that gets into the strain energy of the body. Conservation of energy. And what is the work done? Work done is equal to half sigma Fi acting at Ui, and that is equal to the strain energy, which means U transpose Ku, which is U transpose F, is nothing but 2 times the strain energy. Can the strain energy be negative? Not in general. So strain energy is always greater than or equal to 0. So if there is a body and it is subjected to some forces, it is deformed. There is some accumulated strain energy. You know, strain energy is given as integral E epsilon squared by 2 for a linear elastic body. So it's an integral of a square. E is greater than 0. So strain energy is either 0 or positive. But when is it 0? When there are no strains in the body. But if there are no strains in the body, it means so strain energy equal to 0 means we have rigid body motion. But if you read the question carefully, they say it is in the context of a stable structure. If a structure is stable, say for example, if you consider a simply supported beam which is stable, so this doesn't allow any rigid body motion. But if a structure is unstable, something like this, then it allows a rigid body motion this way. So a stable structure doesn't allow rigid body motion, which means the strain energy is not equal to 0, which means 2 times strain energy, which is equal to U transpose Ku, is always strictly greater than 0 for all possible admissible displacements U, for all kinematically admissible displacements U. So basically, we have proved that the stiffness matrix K is strictly positive definite as long as the structure is stable. So that is one part of the question. So which means we can discard these two parts. Now what are they asking? They're asking about the symmetry of the stiffness matrix. How do we? So you know if there is something called Betti's theorem in linear elasticity and Maxwell's reciprocal theorem. So if you see what they are, they say that if you have a body subjected to some loads and the same body subjected to some displacement field, the work done by the forces, right, the force field of so this is a system 1, this is system 2. The Betti's theorem states that the work done by the forces on this body on the kinematically admissible displacement field in body 2 is the same as the work done by the forces in the body 2 on the kinematically on the displacement field in body 1. So this is statically admissible force field. What is a statically admissible force field? It satisfies equilibrium. And this is a kinematically admissible displacement field. What is kinematically admissible displacement field? It satisfies compatibility. So if you have a body subjected to some kinematically admissible displacement field, so you cannot have a displacement in a deformable body. You can't deform it without applying forces. So there are some forces. Let us call them F2 and delta 2. Delta 2 is known. It's kinematically admissible, but we don't know about the forces. Here the forces are known F1, but it deforms, right? A deformable body will deform. It's not a rigid body, and it gives some delta 1. So the work done by the forces in system 1 on the displacements in the system 2 is equal to the work done by the forces in system 2 on the displacements in system 1. This, if you simplify further, when only one force is acting, you get that the flexibility coefficients are equal. So you get F1 is equal. Fij is equal to Fgi. But how does the theorem actually arise? Let us see, right? By a simple case, let us consider a body like this. And let us consider just 2 points on the body. Let this point be I, this be J. So it's the same body, so you have the node I and the node J. And the body is subjected to some displacement field, right? It is subjected to some displacement field. So there will be a displacement at the here and here. So, but this can be thought of as a superposition. In one case, you hold this fixed and you allow I alone. And in the other case, you hold this fixed and you allow uj alone. And you can superpose both. So what will be the force that is required to cause ui? You need to apply a force of k I ui. And what will be the force that is generated in this support? It will be nothing but kji ui. Similarly, here you will have kij uj, and here you will have kjj uj. So, what is the total strain energy in this body? We have already seen that it is just half into the work done by the forces acting through the displacements. So it is nothing but the strain energy. So before that, let me. So the strain energy. Let us suppose this is applied first, right? Strain energy in one case. So suppose in the first case, ui is equal to 0, then uj is equal to 0, which means in the first case, this is happening first and this is happening second. So in first case, this is happening first and this is happening second. So what happens? So what will be the work done by this? So the work done by this force will be half kjj uj uj. So this is the force and this is the displacement. Is this doing any work? No, because the force is generated when the point is fixed. So the displacement is 0, so there's no work done. Plus. In the second case, what you're doing, you're fixing this point and allowing this to move. So when you allow this to move, there's already a force that is acting here, right? There's already a force of kij uj. Over and above that, this is moving by ui. And this force remains constant as you apply this displacement. Over and above that, there is a force that is applied, which is kii ui. So when so assume this remains constant. You don't assume it actually remains constant as you do this. So you release this and you do this. In that case, what happens? There is an existing force kij uj acting on the displacements ui, and there's no half because there's already existing. It is not increasing as ui is increasing. Plus you have the other force, which is kii ui. So this is the strain energy of the body. If this happens first and this happens, but you can also do it the other way. You can hold this first, apply the force, and then hold this at whatever displacement happened, and then apply this force. In that case, what will be the strain energy? So first you're applying this, so you have half kii ui is the force acting through ui, plus you go there and fix this, so that will not do any more work. But there is already a force generated kji ui, so kji ui is already there, and that is acting on a displacement uj. So this will be an additional work done. Plus you have kjj uj, uj and uj. But you see that these two expressions are not the same. So, but the strain energy is for a linear elastic body. For an elastic body, the strain energy is history independent. This is not true if you have plasticity or any other complicated viscoelasticity. For an elastic body, or rather a hyperelastic body, the strain energy is history independent. It should not matter which load you apply first and which you apply second. The strain energy is history independent. So the strain energies in both the cases have to be equal. So if you equate these two, you see this cancels with this term cancels with this, and you're left with Kij Uj Ui is equal to Kji Ui Uj. Now choose. So this is always true. This is always true, regardless of what displacements you apply. So let us choose Ui is equal to Uj is equal to 1 unit, which means you get Kij is equal to Kji. What does it mean? The displacement, the force at a joint J due to a displacement applied at at I is the same as the force at joint I due to a displacement at J. This is a very powerful result, which means the stiffness matrix. So these are the stiffness coefficients, which means the stiffness matrix is symmetric. So this we have proved. So what is the right answer? The stiffness matrix is positive definite and sorry, not antisymmetric, and it is symmetric. The correct answer is option B. It's positive definite and symmetric. Just an aside, if they didn't say it is stable, then it is called positive semi-definite. That is, it can become zero if there is a rigid body. That is what it means. So let's go to the next question. Which redundant forces or reactions should not be removed to make the structure statically determinate? So this is not relevant to this method actually. You see there are four, so there is a force like this, there's a force like this. These are all reactions, unknown reactions. Now, what is the one of the key ideas? You should be able to solve the primary structure. So if you make the primary structure unstable, it is useless because it will not be in equilibrium. You can't enforce the equations of equilibrium. So you want a primary structure which is statically determinate and stable. So how do you ensure that? You so in this case, if you remove 1 and 2, what happens? If you remove 1 and 2, you will get a structure like this. Yes, this is statically determinate and stable. So this is allowed. And if you remove 1 and 3, what happens? You remove 1 and 3, you get a structure like this. This is removed, right? So you cannot draw this. Yeah, this is also stable, so this is not a problem. And if you remove 3 and 5, right, that is also stable. So 3 and 5, if you remove, we get something like this. That's also simply supportable. Note that the question is which should not be removed. So these all can be removed. If you remove 1 and 5, then you get this. So if you apply even a small horizontal force, this is going to accelerate in this direction. So you cannot remove 1 and 5. So the correct answer is 1 and 5. It should not be removed. Now let's go to the next question. Here we are given a cantilever beam and we are asked to determine the stiffness matrix for this structure. Now there's a small mistake in this question. So this has to be this way. Otherwise, this sense will be. So if this is positive and this is positive, rotations about the z-axis are positive, assuming z-axis comes out of the plane, and vertically upwards y-axis positive. The positive x-axis is in this direction. So now our task is to determine the stiffness matrix for this beam. How do we do it? Let us do it. So let us consider the beam. What are the degrees of freedom? We are not considering horizontal motion. So this is 1 degree of freedom. This is another degree of freedom. Oh, sorry, this is a frame element, right? So So let me draw the degrees of freedom this way. So you have U1, V1, theta 1, U2, P2, theta 2. In this case, let us get the member stiffness matrix. How do we get the member stiffness matrix? As usual, superposition. Now first, how do you get K? So it is a very, very systematic and simple task. And once it is known, you can solve any structure. So what is K11? So K11, let us look at one column at a time. So one column, what does it mean? One column multiplies with U1. So if you say U1 is equal to 1 and all the other displacements are 0, then you will, whatever you get here are the forces that are generated. So first case, let us consider this. I'm fixing everything else. I'm not allowing rotation. I'm putting something like this. This cannot move vertically. So, and you have this. You're applying something like this. So it is very simple. It is a bar under axial tension. So the force that you need to apply in this case is, so if U1 is equal to 1, K11 is what? AE by L. And what is K12? It is in this direction. So this is minus K12. So let me, so the force that is generated here is K at 2 due to no, K21, which is minus AE by L. And what are all the other everything else is 0. So K1J. Just a minute. So these I can redraw them as, let us number the degrees of freedom. So this is 1, 2, 3, 4, 5, 6. So what is K11? K11 is, we just saw AE by L. K12 is 0 because there is no vertical force that is generated by horizontal displacement. K13 is 0, there are no moments generated. Similarly, K15 and K16 are zeros. What is K12? It is in the opposite direction, so it is minus AE by L. So we can directly fill in the first column of the stiffness matrix, which is AE by L, 0, 0, AE by L with a minus sign, 0, 0. What is the second thing? Second column, you need to apply a transverse displacement. And note that the stiffness matrix is symmetric. We have already proved it, so we don't need to compute everything else. So in the second column, how do you do it? You apply a transverse displacement. So except you apply one. So this is what you need to do. You apply a unit displacement here and measure the forces that are generated everywhere else. So we know by the slope deflection method that a moment of 6 EI by L square delta is generated here, which is delta is 1. Here you have a moment of 6 EI by L square. And by equilibrium, you know that there should be an equal and opposite force of 12 EI by L cube. It's quite simple. With the correct sign convention, you can see that K22 is what? How much force you need to apply here to cause a unit displacement? It is 12 EI by L cube. So K22 is 12 EI by L cube. What is the moment that is generated because of a unit displacement? We saw it is counterclockwise, so it is positive 6 EI by L square. Is there any axial force? No. And at node 2, what at the other point, what is the force that is generated? It is downward, so it is a minus 12 EI by L cube. What is the vertical force? It is also minus 6 EI by L square. Sorry, the moment, right? It's not the force. The force is again anti-clockwise, so it is plus 6 EI by L square. Now let us see the third case where you apply a rotation, and that is a direct outcome of the slope deflection equations. So you fix this horizontally and vertically, and you allow a rotation. So how does it deform? It deforms like this. And we know everything from this. What are the moments? So here you have a 4 EI by L. Here you have a 2 EI by L. And you have a net moment of 6 EI by L, which means you need to have shear force of uh, 6 EI by L square. Again, just fill it in. So 3, how much moment you need to apply? 4 EI by L. This axial force, nothing. And here, how much reaction is generated? It is minus 6 EI by L square. And what is the other moment? It is 2 EI by L. Then in the next case, you apply a so everything you repeat for the other joint. So right. So you just have to fix everything else. You apply U1, U2 here. How much force you need to apply? You know from basic mechanics, it is AE by L. So this is again an AE by L. Does it cause any moment or shear force? No, they are zeros. And in the next case, you apply a transverse displacement upwards like this. We know the moments that are generated are clockwise, 6 EI by L square delta. And we have the reactions, reaction forces. So these are clockwise, which means the reaction forces should work anti-clockwise. So 12 EI by L cube. So here you have a minus 12 EI by L cube. So this is a joint. So this is 5, 5. How much force you need to apply here to move it upwards by unit displacement? So it is up. The force is upwards. So it is 12 EI by L cube. And the moments that are generated at this point 5 is clockwise 6 EI by L square. So I have a minus sign. What is the last case? The last case is this. You fix it from translating. You just apply a rotation of 1 unit. And how much moment you need to apply for a unit rotation? It is 4 EI by L from the slope deflection equations. So the last value is just 4 EI by L. And since the stiffness matrix is symmetric, you can fill in the rest by yeah, it is symmetric about the principal diagonal. So I can fill in the rest. So this is 0, 0, 0, 0, and 0. And here you get a 6 EI by L square, a 0, minus 12 EI by L cube, and 6 EI by L square. And this you get a 0, minus 12 EI by sorry, minus 6 EI by L square, 2 EI by L. Here you get just zeros. And here it is a minus 6 EI by L square. Now this is for the entire structure, but look at the support conditions. So the left support is completely restrained from moving and rotating, which means the stiffness matrix is actually multiplying with the degrees of freedom U1, U2, U3, U4, U5, and U6. Note that these are equal to 0 since they are restrained, which means the first three columns are multiplied with 0 coefficients. So these are not really required. So this is not required, this is not required, this is not required. And we know that we enforce the equilibrium equations only at those points where we need to find the degrees of freedom. So this is the submatrix that is of interest to us. Why is that so? Because you will end up once you so these are unknown, and these columns are multiplied. So each row is an equation, and each equation is used for solving for the unknowns. And if you consider the last three rows that are actually useful, the first three columns in the last three rows are multiplied with 0 coefficients, so they do not participate in the solution. Only the last 3x3 submatrix is useful for us. So the matrix for this structural system is AE by L 0, 0, 0, 12 EI by L cube minus 6 EI by L square. And you have a 0 minus 6 EI by L square, 4 EI by L. You can easily see that this matrix is option A. So that is it. Let's go to the next question. So we have a truss assembly of two members. One of them is inclined and the other is straight. An inclined load is applied. So let us first resolve the applied force into vertical and horizontal components. We have and again, this is a mistake. This is not a stable truss. This is wrong. The question is wrong. You need to fix it. And in this, let us mark the degrees of freedom. So the degrees of freedom are like this. So let us take, they have already marked it. This is 3, 4, 1, 2, 5, and 6. And we have the applied forces at this point, which is 50 kilonewton cos 36.87. You know that cos 36.87 is 0.6. So here you have 30 kilonewtons. Vertical component is cos 36.87 is 0.8. So this is 40 kilonewtons. 30 kilonewtons. And this is a 3x5 triangle, 3x4 triangle. So this is 3. So that is it. So now let us consider element by element. Let us consider this as member 1 and this as member 2. And let us do the node numbering as follows. Node 1, 2, and node 3. So in the local coordinate system, we know that for the member BC in the local coordinate system, the stiffness matrix is given by AE by L, 1, -1, -1, and 1. What is L? L for the member BC is 5 meters, 3 square plus 4 square under root. So this is nothing but EA 0.2 minus 0.2 minus 0.2. What is the angle? So this angle is 53.13 degrees. Cos inverse of 4/3. Tan inverse of 4/3 is 53.13 degrees. Now transform this matrix, stiffness matrix, in the local coordinate system to the global coordinate system. What is the transformation matrix, if you remember? The transformation matrix is simple. We have cos theta, sin theta, 0, 0, 0, 0, cos theta, sin theta. And what is KBC global? So KBC global is nothing but T transpose K K member BC. Now, so this angle, if we take for the member BC, let us orient the local. Let us orient the member this way. Here like this. So the first node is 2 and the second node is 3, and it makes an angle of 180 minus this. So it makes an angle of 126.87 degrees. So this angle is 126.87 degrees. That is okay. So if you plug in the values, we get T as transformation matrix as cos theta is negative in the second quadrant, minus 0.6, 0.4, 0, 0, 0, 0, minus 0.6. 0. Now KGBC is minus 0.6, 0.4, 0, 0, 0, 0, minus 0.6, 0.4. There's an EA everywhere. 0.2 minus 0.2, minus 0.2, 0.2. Again, minus 0.6. Just a minute. It's not 0. Cos of this is 0.8. Minus 0.6, 0.8, 0, 0, 0, 0, minus 0.6, 0. You do this multiplication and you can use any calculator. You will get KGBC to be equal to 0.072 minus 0.096 minus 0.072, 0.096, and minus 0.096, 0.128, 0.096, minus 0.128. This will be just negative of the first two, minus 0.072, 0.096, 0.072, minus 0.096. This is 0.096, minus 0.128, minus 0.096, 0.12. So if you compare with the options, you get this is the same as option B. So that is it. Now we'll need this matrix later on. So, but you need to be careful what it relates, right? If we take the angle this way, 2 is the first node and 3 is the second node. So what is the first degree of freedom that in the stiffness matrix? It is 1. So this is 1. This is 2. And what it connects to 5 and 6. So the columns are the degrees of freedom and vertical rows are the forces. So this is important. Let us carry this forward to the next page. Or let it be no problem. Now let us look at the member AC. So for the member AC, the length is how much? 3 meters. So is AE by L. 1 minus 1 minus 1, 1. L is 3 meters, so it is AE into 0.333 minus 0.333 minus 0.333, 0.333. So what is the transformation matrix in this case? It is actually oriented at 0 degrees. So the transformation matrix is simply cos 0 is 1, sin 0 is 0, 0, 0, 0, 1, 0. And its transpose is nothing but the same. So if you apply this onto the member stiffness matrix, you will get exactly the same. So you know very well that this picks the first column and this picks the third column. So you just let us do it. So KGAC will be 1 0 0 0 0 0 1 0 0.333 minus 0.333 minus 0.333 0.333 1 0 0 0 0 0 1 0. So you can see, so this one picks, so it's a row by column multiplication. So this picks the first column and adds a 0 column. Then this picks the second column and adds a 0 column. So we'll see how it works. So you'll get 1 0 0 0 0 1 0 0. So this one picks the first column, adds a 0 row. This one picks the second column, adds a 0 row. So you'll get 0.33 3 minus 0.623 0 0 minus 0.333 0.333 0 0. Do the multiplication again. So what does this do? This one picks the first row, this one picks the third row, and adds 0 rows in it. We get 0.333 0 minus 0.333 0 0 0 0 0 minus 0.333 0 0.333 0 0 0 0 0. There's an EA everywhere. So this is the element stiffness matrix in the global coordinates for the member AC. But what does AC connect? AC connects this A to C. A has the degrees of freedom 3 and 4, and C has the degrees of freedom 1 and 2. So these are 3, 4, 1, and 2. Now let us take these two matrices, right? This one. And the other one. Now these are the element member stiffness matrices in the global coordinate system. Now let us assemble them together to construct the full global structural stiffness matrix. Let us call it K. How many degrees of freedom are there? Totally 6. So it's a 6 cross 6 matrix. So let us look at the first degree of freedom. So where all 1 appears here and here. So how many components are there for 1 1? We have these two. So the first. So just add them up. There's a contribution of stiffness from this and from this. So wait, this is again 3, 4, 1. So this one plus this one is the first element. So it is 0.40533. What is the second element? So 1, 2. How many 1, 2s are appearing? In this, there is a 1, 2. And in this matrix, there is a 1, 2, right? One row, second column. So this. So again, you have a minus 0.096. And look at 1, 3. How many 1, 3s are appearing? So this is 1, 5. It's not 1, 3. So there's only 1, 1, 3, which is 0.333. And there's only 1, 1, 4, which is 0. And how many 1, 5s are there? There's only 1, 1, 5, minus 0.07. And 1, 6 is 0.096. Similarly, repeat the process for 2. So 2, 1. Where is 2, 1? So there's a 2, 1 here, and that is 0. Plus there's a 2, 1 here, which is minus 0.096. So this is a minus 0.096. And what is 2, 2? We have a contribution from here and also from here to 2, 2. So 2, 2 is again 0. It is 0.128. And what is 2, 3? So 2, 3 comes only here, which is 0. Sorry, it is 0. And 2, 4 is also 0. 2, 5. Where is 2, 5? So 2, 5 occurs here, 0.096. 2, 6 is minus 0.13. Similarly, you can fill in all the other values, and it is symmetric about the principal diagonal. So here you have a 0.333, 0, 0, 0, and you have a 0, 0, 0, and you have minus 0.072, 0.096, and you have minus 0.128, and it is symmetric about the principal diagonal. Note that all the coefficients between 3 and 4, right? So between 3, 4 and 5, 6. So whenever you have some association, so this is what is the coefficient? This is 3, 4. That is still okay. And this is 3, 5, 3, 6, 4, 5, 4, 6. They are all zeros because those nodes are not really connected by any member. See here. These degrees of freedom, 3, 4, and 5, 6 are not connected by any member directly. So in the structural stiffness matrix, the coupling between these degrees of freedom is 0. They're not coupled. So we have assembled the total structural stiffness matrix. Now, what is the next step? Look at what degrees of freedom these are getting multiplied with. So you have U1, U2 up to U6. And we saw that in this 3 is equal to U3 is 0, U4 is 0, U5 is 0, U6 is 0. Note, this is not this. This is a hinge support. And in that case, the third column, fourth column, fifth column, and sixth column are getting multiplied with 0 coefficients. Only these two are non-zero. These are all 0 coefficients. So all these are zeros. And right hand side, what do you have? Here you have unknown forces, F3, F4, F5, F6. They're all unknown forces. We don't know the forces because there's a reaction, right? There's a support. We don't know the forces, but we know these forces are how much? The horizontal force is 40, the vertical force is 30. So you don't consider the other equations. You don't because the right hand side is unknown. So you can use these equations to solve for the forces once you know U1 and U2. So first step is to solve for U1 and U2. So consider this system. So the final system that you need to solve for is 0.40533 minus 0.096. That's an EI everywhere. Minus 0.096, 0.128. Acting on U1, U2. These are all multiplied with 0 coefficients, so you need not consider them. It's equal to 40, 30. So what is the answer? So you get U1 equal to 187.5 by EI, and U2 is equal to 375 by EI. So if you see what is asked, they're asking displacements D1 and D2 along the marked degrees of freedom. So 187.5 by EI and 375 by EI. So it's option D. So let's go to the next part of the same question. So the next part, they're asking us to determine the horizontal reaction force at support B. What is that degree of freedom? The horizontal support force, horizontal reaction force at support B, it is F5. We need to find out F5. And how do we determine F5? Now use this. So F5 is actually unknown, and it is given by the equation of the fifth row of the matrix. It is given by this. this is what we need to use. Let us write down the equation fully. Since the matrix is symmetric, the fifth column is the same as the fifth row. Okay. So what is the fifth column? It is, so F5 is nothing but minus 0.072 U1 plus 0.096 U2. Plus there are so many things. 0 multiplied by U3, 0 multiplied by U4, minus 0.072 multiplied by U5, and 0.096 multiplied by U6. But 3, 4, 5, 6 are all 0, so you need not add them. And what is this value equal to? Just plug in these, you get this to be equal to 222.5 kilonewtons. So the horizontal reaction force at the joint B is 22.5 kilonewtons. That corresponds to option C. Next question. So to generate the ith column of the stiffness matrix of a member in a structure, what should we do? So this is also a question in this year's assignment, so I'm not supposed to answer it, but you can see what we have done so far, right? We to generate, so we had K11, just consider this one. Q1, Q2, F1, F2. When will we get F1 alone? When will you get F1 alone? So if you make this, if you make U1 1 and U2 0, you get F1 is equal to what? F1 is equal to K11, F2 is equal to K21. So if you make this 1 and this 0 and measure the forces that are generated by any other method, you can use the force methods or you can use the displacement slope deflection equations, you will get the stiffness coefficients for one column. So if you make 0, 1, you will get, in this case, you will get F1, F2. You measure them, they will turn out to be K12 and K22. So you can see which option it corresponds to and answer them. You can see which option it corresponds to and answer them. Since it is there in this year's assignment, I'm not giving this exact answer, but this is the procedure. This is what we did and this is how it works. So let's go to the last question for the day. So this is the last problem. There are 3 sub questions in this. Before that, before we get to frames, let me know if there's any doubt, whatever I covered so far. Is there any particular doubt?
Sir, actually, I have a question related to moment distribution method.
Sure. Yes.
Sir, in this year's GATE examination
Okay.
afternoon batch, there was a question. Uh, uh, can I means it was a symmetric frame, so my doubt is related to that. Can
Okay.
I tell you about the link from where you can find the question?
Yeah, sure. You can even paste the question in the chat box if you have this.
Actually, I'm not able to means get onto the chat box.
Oh, okay. Uh, Let me see. Is there any settings?
I have used my browser to open the meeting. I think
Oh,
that's the reason why I'm not able to do so. Sir, I can tell you if you open Google to search that.
okay.
Sir, it's GATE 2023 question paper made easy. Uh, Download. No, sir, not this one. It's
Uh,
a solution. I think. You can go to Made Easy solution.
Solution. Okay.
Yes, sir, with detailed solution first one.
This one?
Yes, sir. In the afternoon, yeah, first one, yes, sir.
Afternoon session. Okay.
Yes, sir.
Civil, yeah. Okay. So which one is it?
Page number 36, sir. Question 54.
Okay. So for the frame shown in the figure, all members have the same length. Beams GBG, magnitude of the moment reaction at A is what is the value of K?
Sir,
So should
here,
I look at the
here
solution? Yeah.
they have KBC. The stiffness coefficient is KBC by 2. Why, sir?
Oh, okay, okay.
Stiffness.
Okay, I get your question. So the reason is, let me tell you. We have seen it in the last class. Let me add a page. Week 10. So when you have this, this is a joint. You have a joint like this. And here, because of symmetry boundary conditions, you are replacing it with a guided ruler. That you understood, right?
Yes, sir.
Yeah. You see why a guided ruler is suitable for a symmetric boundary condition, because the symmetric condition is u is equal to 0. Sorry, the horizontal displacement have to be 0. V can be anything. V is not equal to 0. The force has to be 0. Fy should be 0. And theta should be 0. So these are the symmetry boundary conditions, and this is satisfied by the guided ruler. But
Sir,
once you have,
why
yeah,
V isn't equals to 0?
you should look at the way the structure deforms. So the structure is something like this. I have UDL somewhere like this. So it will deform in a symmetric fashion. So this is how we expect it to deform, right? So why V is not equal to 0 is V doesn't actually, in general, nothing is 0. But the shear force here has to be 0. I'll tell you why. If the shear force is not 0, let us say the left part of the beam has a shear force V like this. Then the right part of the beam has a shear force equal and opposite like this. But it is symmetric, which means if you flip this side to this side, nothing should change. So if you look at this, let me draw a better picture. So symmetry boundary conditions, are like this. So you have a symmetric structure like this, subjected to symmetric loading. So in this case, we have something like this. Suppose it deforms this way. You take, and they are marking this as the symmetry line. Symmetry means if you flip the two sides, then nothing should change. So if you draw an enlarged view here of the two parts there, right? You have, if you cut the structure at that along the symmetry line, what all you can have, you will have an axial force, you will have a bending moment, and you will have a shear force. Now, since it is a symmetry line, if you take a mirror, right? You take a mirror and place it along this line, then you should see exactly the same on this side. That is symmetry, because the structure is deforming exactly the same. If you see the bending moment, it is exactly what you see in a mirror. The axial force, it is exactly what you will see in a mirror. but the shear force is reversing its direction, which means this is the same as the shear force on the left hand side is the same as the shear force on the right hand side. So, but since it is shifting the direction, only if it is zero, it can obey the symmetry condition. That is the idea. So if it is non-zero, then it is not symmetric. The deformation is not symmetric. But we know since the geometry is symmetric and the loading is symmetric, the deformation, stresses, strains, displacements, everything will be symmetric about the center line. But if the shear force is not symmetric, then that is violating the symmetry condition. So shear force has to be necessarily zero. So that is one condition. So one condition is the shear force should be zero. What about the displacement? If the shear force is zero, then the displacement is not zero, right? We don't know anything about the displacement. Displacement can be zero or it can be non-zero. We don't know that. So the displacement in the vertical direction is not necessarily zero. What about
The moments
yeah?
must also be equal to zero, and the axial force must also be equal to zero.
That is not so. The reason is if you flip it, you should have the same structure. That is, if you flip this side to this side and this side to this side, you should have the same structure. That is what I'm telling, right? So the moment if you place a mirror along the symmetry line, right? If you place a mirror along the symmetry line and look into the mirror like this, the moment you see will be exactly like this. What is there on the other side? But if you look at the shear force, it is reversing the direction, right? If you have an object like this, if you look at the mirror, you will see exactly the same thing. If you have an object like this E, if you look at the mirror, you will see this. But if you have an object like this, you should see this.
Yes, sir, I'm getting.
Yeah. But the shear force is shifting its direction. It's like this. You're not seeing this. So shear force has to be zero. Similarly, what about the horizontal displacement? So this is about the forces. If you see the horizontal displacement, if this is moving in this direction, it means this line has crossed the symmetry line and gone to this side after deforming. But if you see from the other side, it means something has got into this. Again, it is violating symmetry. So U has to be zero, which means N doesn't have to be zero. The normal force doesn't have to be zero. Similarly, if you're having a rotation like this in clockwise direction, from the other side, it will look like it is going down. So here it is rotated this way. And from the other side, you will see an upstream, and here you will see a downstream. So rotation is zero, which means moment is zero. So you can replace here with a this point with a guided ruler. So this is replaced with a guided ruler. And now you are asking why the stiffness is divided by 2, right? So I'll tell you. So now how do you determine the stiffness coefficients? You take it this way. So let us write down the slope deflection equations here. So let us take it as span AB. What is MAB for the span? MAB is 4 EI by L theta A plus 2 EI by L theta B. But since its rotation at this point is 0, it is 0. But it can have a delta. It can have a delta. Minus 6 EI by L square delta. And what is MBA? MBA is 4 EI by L theta B, which is 0, plus 2 EI by L theta A minus 6 EI by L square delta. Do we know anything about MAB and MBA? No, both of them can be non-zero. But what we do know is the shear force has to be 0. We are going to use this symmetry condition. Shear force has to be 0. What is the shear force in this beam? There is no internal loading. So if you draw a free body diagram, you have MAB, MBA, and since there's no internal loading, we'll have equal and opposite shear force. V and V to counteract like this. So what is V equal to? V is equal to minus of MAB plus MBA. So V acting into L, equal and opposite forces separated by L, so divided by L on both sides. Right? This should be equal to 0. Now simply add both. What do you get? 4 EI by L plus 2 EI by L is 6 EI by L. We'll get 6 EI by L theta A. And add these two. We'll get minus 12 EI by L square delta is equal to 0. Now from this equation, you can eliminate delta, because delta is not easy to use in a moment distribution method, right? In moment distribution, we lock and unlock the joint rotation. So delta is always, it's not easy to use in moment distribution. It's okay in slope deflection or displacement methods. So you eliminate delta. So delta is equal to what? You'll get delta is equal to theta A by 2L. You solve this. Now go and put it back in the expression for MAB. Now what is MAB? So MAB is 4EI by L. Just a minute. This is L square, right? So it's not by L. It is L theta A by 2. Units. So this is in radians, this is in meters. Minus 6 EI by L square. Into delta, and where delta is theta A by 2. So this is nothing but 2 EI by L. Sorry, 4 minus 3, it is 1 EI by L. Right? So MAB is 1 EI by L theta A. So everything is multiplied by theta A. Now note that L, whatever L we took is actually half of the length of the full beam. So we have only taken half the length. So if the full beam length is L, let us say this is L naught, here it is L by 2. L is equal to L naught by 2. So what is the relation here? MAB is EI by whatever L original length by 2. So get something like this. So what is the stiffness factor here? So K is equal to 2 EI by L, which is half of the stiffness of the full beam. So which is half of K naught. If you didn't apply the symmetry boundary condition, you would have taken 4 EI by L. But since you applied symmetry boundary condition, it is becoming 2 EI by L, which is half of the original value. So that is the reason they have taken half. Is that okay? You understood?
Can you repeat about the boundary conditions that you were talking about?
The symmetry boundary condition?
Yes, sir.
So I said that if you have a line of symmetry and all the forces, right? If you have a force like
Sir,
this.
upward.
Upward. Which one? This one?
Yes, sir. U equals to 0, V equals to... Please explain this part again, please.
Oh, okay. That is what I said. So if you have, I'm saying, so the structure is deforming symmetrical.
Sir, U is the
Horizontal displacement.
horizontal displacement, V is the vertical, and theta is the rotation.
Rotation, yes. So if you take if you take this point, if this point is moving to the right hand side by some U, but the structure is symmetric, right? Which means if you consider the left half is going like this with some U, then the right half has to come this way. But this point cannot have two different displacements. It has to be symmetric. So if it is moving towards the right, this should move towards the left. But is that allowed? No. Why is that not allowed? It means the point has to go into each other, right? If this is going this direction, the left, if there is a net U, the structure still has to be symmetric. If the left half is deforming like this, the right half will deform like this. So if there is a U here, if there is a non-zero U here, exactly same amount of U is happening here also. But this point is the same point. So here you cannot have a plus U and here you cannot have a minus U for the same point. So if you say plus U is equal to minus U at that point, which means U is equal to 0. Similarly,
Sir,
theta.
can I explain what you are trying to say?
Yes.
If I am getting it or not. Sir,
Yes.
Due to the loading condition, what I am
Yes.
getting from you, due to
Yes.
the loading condition, the left hand side, left part or the right part will deflect in two different ways.
Two different ways, but in a symmetric way.
But since it is a symmetric condition, so
Yes.
they won't deflect.
Yes.
Uh, is that correct? What you are trying to
Symmetric
explain?
means basically if you keep a mirror, whatever is the deflection on the other side will be seen in the mirror. That's what it means.
Yes, sir.
So if this,
Since the loading condition is not means unsymmetric, if we cut out, then it is in a form of unsymmetric way. What I'm trying to.
okay, you should see symmetry before cutting. So cutting we do only if there is symmetry, right? if it is symmetric, if the loading is symmetric, if the geometry, so if geometry and loads are symmetric, it is not only linear elasticity, whatever it is, non-linear plasticity, whatever it is, if the geometry and the loads are symmetric, you can always analyze half of the model. So just take the simple case of portal frame, right? If you have this is geometry and loads are symmetric, which means if you place a mirror in the middle, the way this deforms, exactly the mirror image will be the deformation of the other half. That is the idea. So that is what I used here to reason out. So if this is deforming in this manner, then if it has a deflection in the right hand side, the right half will have a deflection in the left hand side because it's a mirror image. But the point on the mirror cannot go on both sides, right? So if this half has a deflection of u plus, this will have minus u. But if u should be equal to minus u because it is the same
Yes,
point.
sir, I'm
Yeah.
getting. Actually, what I was trying to say, I was searching in my notebook what exact word.
Okay.
Actually, when we cut it out, then
Yes.
due to the there will be a sway due to unsymmetric loading condition when we
Yes.
cut it out.
Yes.
But since it is joined, so there should not be any sway.
Yes. Exactly.
Uh, that okay, sir. Please move forward. Explain. Explain further, please, sir.
Yeah. So u is 0. If there is a sway, the other half will sway in the other direction, but the point is the same point. So you cannot have two different displacements for a point. So it should be 0. Now what about theta? So theta is, now you see here, right? So if you see on the left hand side, suppose the beam develops a slope like this. The right hand side will have to develop a slope like this. So if this is theta, this should also be theta. And this is a mirror image. The deformation is symmetric. This is the exact mirror image. This side if you have theta, this side if you have theta. But in that case, what happens to the beam at this point? It generates a cusp, right? It's a sharp discontinuity. The beam is not differentiable. It's a sharp uh, thing. So if it's like an internal hinge, the slopes are not continuous. So if you have theta, if the beam is continuous, it has to continue this way. And similarly, this side, if you have a theta up, so this is a theta in the clockwise direction, and this is a theta in the counterclockwise direction. So there's a jump in the slope if theta is not equal to 0. So to avoid that, right? So symmetry condition is more stronger than a sway frame. So we are having this, right? You're loading it this way. How does it deform? Say it deforms something like this. Now I have purposefully drawn it such that there is a slope here. There's a slope here, which is say counterclockwise. But if you interchange, if you take the mirror image of the structure, right? If you take the mirror image of the structure about this point, you will get this. Something like this. Now, in this case, the rotation at this point is downwards. But what did we see? If we take the mirror image about the symmetry plane, in both the cases, you should get the same structure, which means theta is equal to minus theta. And that cannot, and if you take this theta to the side, you get 2 theta is equal to 0. So theta is equal to 0. So along this plane, if you have a u and you take a mirror image of the same structure about the symmetry plane, the u will become minus u and theta will become minus theta. But v will remain v only. That is the beauty. So v will remain v only. If it deflects upwards, since it is lying on the mirror plane, it will remain v only. So v will not be 0. U will be 0. Theta will be 0. V will not be 0. For the same reason, if you take a mirror image, plus shear force will become minus shear force, right? Initially, if it is like this, once you take a mirror image, it will become like this. But that is wrong. Here, if the shear force is V, here it's minus V. But that cannot happen since the structure is symmetric. So V, if it is equal to minus V, the shear force, then V is also equal to 0. But bending moments, if you see, the axial force is like this, bending moment is like this. If you take a mirror image of this, about this line, you will get the same thing exactly. So those doesn't have to be equal to 0. You got it? Is that okay?
Yes, sir. You are trying to say that theta will be minus theta.
Yeah.
Theta uh, V is there is a means vertical movement upward due to the as we can see in the deflected shape. So
Yes.
but the shear force must have an upward and downward direction so that they must be equal to zero.
Yes.
Means
Yes.
the sum of that. So that's why V equals to minus V. Okay, okay, sir.
Yes. If
And
you take a mirror, yeah.
theta should be zero.
Yes. Basically, whenever you have a symmetric boundary condition, take a mirror image and see if anything is flipping sign. Theta is flipping sign, U is flipping sign, shear force is flipping sign. But bending moment and the axial force are not flipping their signs. So whatever is flipping their signs have to be 0. Because 0, if you 0 is equal to minus 0, right? So that is the only value which will not change even if it flips sign. So that is the idea. So I can go ahead, right?
Yes, sir. You can use the previous slide only. You don't need to write again.
Okay. Yeah. So and then you got this why the stiffness is half. Is that okay? So 2 EI by L, you got it right?
You used the slope deflection method to get it.
Yeah, I used the slope deflection method and I enforced that the shear force is 0 and I got a relation between delta and theta and substituted back into the moment equation. So we get something like this, but L is actually half. So you get L naught L by 2, but this 2 EI by L is actually half of 4 EI by L. So it is K is equal to half of K. That is how they have used it.
Sir, there are certain tricks that are being used in these questions. Sir, from where I think some coaching institute can help for these things. And,
Yeah, tricks, as you do more and more problems, it will become very clear. So, and those, even if you don't know the trick, you can use the slope deflection equations to get it right. So it helps in only the speed of solving problems. But yeah, if you have to,
sir, I can see that the moment distribution method can be used where there is some numerical value, where there is some means some V, W or something like that is being used, then or Q is used, then slope deflection method is quite useful, or
yes,
other
yes,
any other method.
slope deflection method is quite useful. So slope deflection. So slope
Sir, I am
deflection.
seeing that in some questions they are using Castigliano's theorem or whatever the pronunciation is
Okay,
uh, instead of force method or any other method. So that was not covered in the lecture series, but I get what what is there in that concept.
okay,
So there are certain more things which are not covered in the lecture series. Uh,
okay.
and there are portal frame method, cantilever method, the approximate methods, and I think yes, sir. Yes, sir. Yes, these things were not covered.
Yeah, yeah. Since it is a just a 12-week course, I think probably professor couldn't cover it. Yeah, if it's a full 1 semester course, maybe it would be done. So slope deflection, you can use it when you have, and the degree of static indeterminacy is very high and kinematic determinacy is low. And it will be helpful when you have symbolic like W, P, M without numbers, right? If you have symbols, it is helpful. Moment distribution is useful, as you said, correctly, only when you have numbers because it's an iterative method. It relies on continuously decreasing error when you do the iterations. So that is not useful when you have W, P. And also, if you have a sway frame, slope deflection method is much, much better than moment distribution because you need to do multiple cycles of moment distribution if you have a sway frame. So in those cases, you can use slope deflection methods. And tricks, if you ask, yeah, you can look at any of the books in structural analysis. There will be this symmetry, anti-symmetry. These things will be clearly described. But other things like this half K naught, those things you have to like It comes by practice. Is that okay?
Yes, sir. Yes,
Yes.
sir. Thank you.
Yeah. So let me proceed with the other problem for the day. So we have a beam. It's a simple problem. We don't need to do any transformations. Uh, so we have a two-membered beam. Sorry, I shouldn't. This is not an internal edge. Okay. And this is statically indeterminate to the second degree. And this is L. So this is 4 meters. This is 2 meters. It is not to scale. This is EI by 2. And this is EI. And you have an applied moment of 20 kilonewton meters. What is the first step? Identify the members. This is member 1, member 2. And put the nodes 1, 2, and 3. Let us write down the member stiffness matrix. It is very simple. We have done it already for the frame member, frame member in the previous exam, not in the previous one. The third question, right? You have already done it for the frame member in the third question. So let us just reuse it. Okay, never mind. I'll rewrite it, no problem. So for a beam member, say this is a beam element. If you have, there's no horizontal movement. It's a transverse beam. So this is 1. This is degree of freedom 2. Similarly, this is 3. And this is the degree of freedom 4. For this, again, we have already done it, right? How do you determine 1? You do this. This. So to determine 1, keep everything else fixed and apply 1. So you got that 6 EI by L square and so on. To determine 2, you apply a moment, keep this fixed. You get something like this. And this will be 4 EI by L and so on. So this is, you'll get 12 EI by L cube, 6 EI by L square, minus 12 EI by L cube, 6 EI by L square. This is for the shear force part. And what are the moments? You know very well. Because of a unit applied displacement, you get a moment of 6 EI by L square counterclockwise. Because of a rotation, you get a moment of 4 EI by L. Again, 6 EI by L square due to the other side rotation. And due to the other side rotation, here by the slope deflection equations, you'll get 2 EI by L. And this will be negative of it, minus 12 EI by L cube. Let me see. Minus 6 EI by L square. Minus 12 plus 12 EI by L cube. And it is symmetric, right? So this will be minus 6 EI by L square. The last row will be 6 EI by L square. 2 EI by L. 6 EI by L square. Minus 6 EI by L square. 4 EI by L. This can be obtained easily by using the moment slope deflection equations. So this is the beam element stiffness matrix. So for the first beam, for the beam AB, you can easily write it down. So the member stiffness matrix for the beam AB is what? EI is EI, L is 4 meters, so 12 by 4 cube. So you get, let me just plug in the value since we are running late. So let me just plug in the values. So 12 EI by L cube is 3 by 16. 3 by 8 minus 3 by 16, 3 by 8. So 6 EI by L square is 3 by 8. This is 1 minus 3 by 8. And this is half of this, right? So it is half. So this is minus 3 by 16, minus 3 by 8, 3 by 16, and minus 3 by 8. And this one is 3 by 8. 2a by L is already, we got it, half, it is symmetric. So minus 3 by 8 and 1. So this is the, everything is multiplied by EI. Similarly, for the member BC also you can write. Just note that EI is EI by 2 and length is 2 meters. So just plug in the values. So for the member BC, you get EI into 3 by 4. It's a matter of just plugging in the values. So I'm not spending time on this. Minus 3 by 4 and 3 by 4. Next row is 3 by 4, 1, minus 3 by 4 and half. So as usual, this is the negative of the above. 3 by 4 and minus 3 by 4. The last one is 3 by 4, half, minus 3 by 4. Now the important part here is note that all the beams are horizontal, so we really don't need to transform it to any other coordinate system. But what does it relate? So based on this node numbering of the degrees of freedom, this is 1, this is 2, this is 3, this is 4 forces. And this is 1, 2, 3, 4. And here 3, 4, 5, 6, 3, 4, 5, 6. So we got, so what are they asking? They're asking us to determine the correct stiffness matrix of the member AB. So 3 by 16 is 0.1875. So it's either B or C. And you see that minus point, yeah, here you are having a 1. So it is option B. Now let us construct the structural stiffness matrix. So how to do it? So you have K11, assemble everything together. There's only one term, only 3, 4. So you see here, only this matrix is repeated. So split this into 4 parts. You see that these are the members that are repeated in both the matrices. So this contributes to the structural matrix 3, 3, 3, 4, 4, 3, and 4, 4. And here also you have the contributions to the structural matrix 3, 3, 3, 4, 4, 3, and 4, 4. All other elements are occurring only once, so you can write down the structural stiffness matrix like this. So here you have 1, 2, 3, 4, 5, and 6. And the values are 3 by 16. So the first thing is unchanged, 3 by 16, 3 by 8, 3 by 8, 1. The first submatrix is unchanged. Even this is unchanged, 3 by 16, 3 by 8, minus 3 by 8, 1 by 2. The rest are zeros. Because why? You can see 1, 2 is not interacting with 5, 6 by any direct member. So those are zeros. By symmetry, these are also zeros. And by symmetry, these are also 3 by 16, 3 by 8, minus 3 by 8, 1 by 2. And let me fill in the others, 15 by 16, 3 by 8, 3 by 8, 2. Here we have minus 3 by 4, 3 by 4. 3 by 4, minus 3 by 4, half. So again, it is symmetric. So this is minus 3 by 4, minus 3 by 4, 3 by 4, half, minus 3 by 4, and this is 3 by 4, minus 3 by 4, and 1. So 1, 2, 3, Okay, so this is the global stiffness matrix. Now let us see what are all the required things, right? So we know that U1 is 0. So what are the boundary conditions? U1 is 0, U3 is 0, and U5 is 0. All the vertical displacements are zeros. We only need the rotation degrees of freedom. So this column is going to multiply it by 0. So this column is going to multiply by 0. This column is multiplied by 0. This column is multiplied by 0. And what do we have in the force matrix? We have U6, the last one is minus 20 kilonewtons meter. And this we don't know. So 5 is unknown. F5 is unknown. And F4 is what? F4 is also, there's no applied moment here, right? There's no applied moment here. So that is 0. And F3 is unknown. There's no applied moment here. 1 is unknown. So don't consider the internal moments. We are only dealing with the applied moments. Internal moments cancel out each other. So they don't contribute to the equilibrium of the joint. So these equations are fully known. This one, this one, this one, and sixth equation. So select those and let us write down the reduced system. So the reduced system is, we only want 2, 4, 6, 2, 4, 6. So that if you see it is 1, 1 by 2, 0. You have an EI everywhere. 1 by 2, 2, 1 by 2, 0, 1 by 2, 1. What is it multiplied with? It is multiplied with U2, U4, U6. These are non-zero values. These are actually the slopes. Is equal to 0, 0. So it's a 3x3 system of equations. You can solve it using your calculator. And you get U2 is equal to minus 10 by 3 EI. U4 is equal to 20 by 3 EI. And U6 is equal to minus 70 by 3 EI. It is given that it is given in the question E is 100 GPa and I is 1 into 10 power minus 7 Newton meter square. So EI is 100. So EI is 1000. 10,000 kilonewton meter square, 10,000 Newton meter square, which is nothing but 10 kilonewton meter square. So, and U6 is nothing but 70 by 3 into 10. So kilonewton meters. So it is nothing but 2.332 radians. And that is option C. So that is it. So U6 is 2.332 radians. But note that this is a very big angle. So this is even greater than 90 degrees. So pi is 3.14 and 2.332 radians is a very big angle. It's an obtuse angle. So basically this solution is not valid since we used linear elasticity. But it's okay as an exercise. This is okay. But in reality, if you're getting such a solution, you should discard the answer. Means the theory is not correct for the problem that we just saw. Now they're asking the absolute vertical reaction at support B. How do we determine it? So let's go to the previous page. Support B vertical reaction is F3, right? So what is F3? F3 is 3 by 16 U1 plus 3 by 8 U2 and so on. But we know U1, U3, U5 are zeros. So you get it as so F3 is equal to 3 by 8 into what is U1? U1 is minus 10 by 3. Sorry, U2, right? 3 by 8 into U2 plus 3 by 8 into EI gets cancelled. 3 by 8 into 20 plus 6. 6 is minus 70 by 3. So determine what answer you get. And that turns out to be 13.123. So 10 by 8 is 1.1. Is it 10 by 8? 3 by there's a minus sign. It's a minus sign. So you get so this is 10 by 8, 1.25 plus 1.25, and 70 by 4 is wait a minute. So 70, 1.25. This is 70 by 4, which is 35, 17.5, and 20 by 8 is 2.5 plus 35 plus 17.5, which is minus 2.5 minus 17.5, which is just a minute. Check the stiffness matrix. 2, 3. So 2, 3 is minus 3 by 8, and 3, 2 is also minus 3 by 8. That is okay. Yeah, so plus 10 by 8. So it is 13.75. The answer is minus 13.75 kilonewton, which means they are actually having a pulling force, downward force. So take it to the next page. The correct answer is 13.75 kilonewtons. Absolute value is for the options. So that is the end of today's session. Thank you everyone for attending. If you have any doubts, you can ask. You can ask in the Q&A forum, or also you can also add as a comment in the YouTube page. So this completes all the problems for the assignment. So your assignment ends this week. The 12th assignment is due by this Wednesday. And next week, I will be trying to give you some revision for the exam, final exam. I'll try to cover all the topics from the beginning to the end, a quick brush up, and a few problems as usual. So in case you need anything in particular, you want something something to be solved in particular, you can post it in the forum or in the YouTube comments page. So I will address it in the next session.
Sir, what is the research that you are doing?
Just a minute. Let me stop this recording. Then I'll, because the video length is very long. So thank you everyone.